In string theory, the whole universe is made of these tiny vibrating strings. But here's the thing. Just like a guitar, a quantum string can't just play any random note. It has a very specific set of allowed vibrations, what physicists call its spectrum. Today, we're going to dive into how they figured out this cosmic playlist, and in the process, had to banish some pretty spooky mathematical ghosts. I mean, it's the most fundamental question you could ask in the theory, right? When physicists first tried to write down the math for a single quantum string, the answers they got back were, well, they were deeply strange. They described a universe of possibilities that just didn't quite make sense. Yeah, you heard that right. The very first attempt at a theory was haunted. Its own mathematics predicted things called unphysical states, or ghosts. These were string vibrations with just nonsensical properties, like having a negative probability of existing. Now, a theory that predicts impossible things is a broken theory, and this problem really threatened to unravel string theory before it even got started. Okay, so let's get into it. Here's our roadmap for today. First, we're going to take a closer look at this whole ghost problem. Then we'll check out the first kind of brute force attempt to fix it, which is called OCQ. After that, we'll see the much more elegant solution that came along and really explore the power of a tool called BRST. We'll see how this all led to the no-ghost theorem, and finally, what it all means for the music of reality. First up, let's get properly acquainted with the main villain of our story here, the ghost in the quantum machine. So, to really understand the problem, we need this concept called Hilbert space. Now, it sounds complicated, but you can just think of it as a giant library that contains every single possible state a quantum system could ever be in. It's the complete list of all possible answers to the question, what is this string doing right now? And here's where the trouble started. The initial Hilbert space for a string is just way too big. It's like that library is filled not just with valid books, but also with complete gibberish, books with negative pages, and books that just flat out contradict the laws of physics. These are the ghosts, and they absolutely had to be removed for the theory to have any chance of describing reality. So, physicists obviously needed a way to clean out that library of impossible states. Their first method was a bit of a kludge, honestly. The source material describes it as an ad hoc approach. It's called old covariant quantization, or OCQ for short. The whole idea behind OCQ was basically to go through the library by hand. First, you just impose some specific rules to define what counts as physical. Then, you find these things called null states, which are technically physical but have zero impact, kind of like a silent note in a song. And you decide that any states that only differ by a null state are basically the same thing. It really was a brute force way of weeding out all the nonsense. Now, here's where things get really interesting, the unexpected punchline. For this whole procedure to actually work, for it to consistently get rid of all the ghosts, the math demanded a shocking condition. Space-time must have 26 dimensions. This wasn't something they put in by hand. It just fell right out of the equations. It was a bizarre result for sure, but it was also this tantalizing clue that the ghosts weren't just an error, but a signpost pointing to a much deeper truth about the universe's structure. That strange requirement for 26 dimensions. That was the key insight. It meant the ghost problem wasn't just some bug that needed to be patched. No, it was a feature, and it was pointing to a hidden symmetry in the theory. The brute force OCQ method stumbled onto this clue, which then kicked off the search for a much more elegant approach that could explain why it all worked. And this really lays out the difference between the two approaches. OCQ was an ad hoc fix that just manually deleted bad states. The new method, BRST quantization, was a systematic cure. Instead of just throwing states out, it used a deeper symmetry of the theory to naturally identify which ones were the right ones all along. The BRST method is just so beautiful because it doesn't impose rules from the outside. It uncovers a hidden symmetry that was there the whole time and uses it as a natural gatekeeper, cleanly separating what's physical from what's not. So, the hero of this new, more elegant story is an operator called the BRST charge, which we'll just call QB. You can think of it as a kind of quality control inspector for quantum states. It's built directly from that fundamental symmetry, and its whole job is to test every possible state to see if it's physically legitimate. The crucial point is this first rule. A state is physical if the BRST charge, when you apply it to that state, gives you a result of 0. In other words, Q sub B annihilates the state. If it passes that test, it's physical. If it doesn't, it's a ghost. Simple as that.
The second rule is all about cleaning up redundancies. If you take a physical state and add another state that is itself the result of QB acting on something, the new state is physically the same. It's exactly like the difference between C sharp and D flat on a piano, two different ways of describing the exact same physical note. This is the elegant, systematic way to handle those null states from OCQ.
So with these two powerful and systematic rules, physicists were no longer just patching holes in the theory. They could now rigorously prove, once and for all, that string theory was a consistent, ghost-free framework. And the climax of this entire journey, the grand proof itself, is a landmark result in theoretical physics known as the no-ghost theorem. The no-ghost theorem is really the ultimate guarantee. It proves that the set of states that pass the BRST test has a positive inner product, which means no more negative probabilities. All the ghosts are gone. It also proves that the spectrum you get is identical to the one you get from other methods. And, critically, it confirms that this beautiful, symmetric structure only holds together if spacetime has, you guessed it, 26 dimensions. So why does all this intricate mathematical housecleaning actually matter? I mean, what does finding the string spectrum really mean in the grand scheme of things? It means everything. It's the physical rulebook. The BRST formalism provides the framework to figure out the allowed vibrations, the actual notes that a fundamental string can play. Out of an infinite, ghost-filled library of possibilities, nature selects a specific, harmonious, and consistent set of states. And as the source material makes crystal clear, this isn't just a one-time fix. This quote highlights that the BRST method is an absolutely essential tool for pretty much everything that comes next. To understand how strings interact, how they scatter off each other, you need the full power of this ghost-busting machinery. So we've gone from a theory literally haunted by ghosts to a consistent picture of the fundamental notes of reality. We have found the allowed chords in the music of the universe. And that leaves us with a final, absolutely tantalizing question. What happens when these strings start playing together?